Hi there, welcome to Math 7. This is Unit 2, Lesson 1, called One of These Things is Not Like the Others. Today's lesson focus was talking about and remembering what equivalent ratios are. Now this is something you talked about potentially in 6th grade at some level. And so some things we're going to be talking about today were what we call equivalent ratios. We'll also talk about perhaps a little bit of some unit rate. And that unit rate is something, again, back from 6th grade when we're talking about one of something. Equivalent ratios, we've talked about that a little bit before, are going to be a variety of comparisons that show how things are related to one another. And so we're going to look at unit rates today. We're going to look at equivalent ratios. We've already talked about scale factors in our previous unit. And scale factors, you're going to see eventually, have something in common with these equivalent ratios. So we'll get there in a second here. But let's take a look at how your lesson began. You started with, first of all, remembering double number lines. And this might be new if you're new to the series. You may not have done a double number line last year, but here's how double number line works. Is you take two elements, and what you're trying to do is you're trying to look at a pattern for the first one and then see what the pattern would be for the second one. And as you compare two different patterns, you end up with a ratio here, like something like 2 to 1. So for example, in this case here, I have 0, something, 2, something, something, something. It looks as though I'm counting up by ones here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm certainly counting up by ones on the top line. If I'm counting by ones there, I'm still going to count by ones here, except I notice that it's 0, and then I have a half, and then a 1. This would be 1.5, making this space 2, 2.5, 3, 3.5, 4, 4.5, 5. By doing this here, what it shows me is that I'm going to be able to form a series of equivalent ratios. 2 to 1 is going to be comparable to 4 to 2, just as 6 to 3, 8 to 4, and eventually here 10 to 5. 10 to 5. And if you think back to what we did in our previous unit, we're looking also at how can I kind of change things from a 2 to a 4. In this case here, it'd be by multiplying by 2, right? So to go from here to here, I'm multiplying by 2. To go from a 2 to a 6 over here, I'm multiplying by 3. Well, is that what happens here? It sure does, times 3. And so we see that when we multiply by, we might want to call it a scale factor, but we're not here. We're talking about a rate of some sort. We're going to be able to take these equivalent fractions and make sure we can prove that they are all equivalent to one another. And so a double number line or tape diagram can help you see which ones line up with each other, and then perhaps sometimes which ones don't. All right? So let's take a look then at your next thing you did in class. Is you had some mystery mixtures today, which hope you had a good time doing that. In that little activity, you were provided with several things. You were given some ingredients like these ones here, where you were given some mixture and some water and a measuring spoon and teaspoons in order to make a variety of drinks to see what was similar and what was different between them. And when you did that, what you had is you had 3 different drink mixtures. One was made with 1 cup of water and 1.5 teaspoons of flavoring. Another with 2 cups of water and a half a teaspoon flavoring, and one with 1 cup and a 1/4 teaspoon of flavoring. And the idea there, hopefully, when you went through this process, was when you tasted the different drinks, you discover that 2 of them seemed to taste pretty much the same, and another one was quite stronger than the others, perhaps sweeter, more flavorful. However you want to describe that, that was up to you. You can even see in our picture here that our colors are different. I have a pinkish color here where I have a little darker red there, indicating that there's more of the flavoring in this one than there are in the other 2 drink mixes. And so you did that in class today, and hopefully you enjoyed that, and it was kind of fun to be able to drink some fun drinks in class. And from that then, you moved into then question about, all right, well, let's look at another recipe. If you had another recipe that wanted you to make some mixtures, what would happen with these things here? So in this case here, if I had 1 cup of water, and let's go ahead and just draw a cup. I'm going to draw a picture here. 1 cup of water, and then I had 1.5 teaspoons, and this is the same, well, this is the same one, I'm sorry. So you had 1 cup to 1.5 teaspoons. So that's going to be, if I did a teaspoon, I could say, let's make a teaspoon shape like this, teaspoon and a half. So I had a whole cup here, and then for the teaspoon mixture I had 1.5. Here we had 2 cups, 2 cups, 2 cups, this is my cup section, and I had half a teaspoon. And then over here I had 1 cup. I didn't have a half, I had a quarter, which would be like taking a half and just doing half of a half. And so when you look at that, you can see that, well, from here to here, I'm doubling it, right? I'm multiplying by 2 to go from 1 to 2. And over here, if I had a quarter, doubled times 2 becomes 2 over 4, which becomes a half. So when I multiply by 2, I do end up with that half one there. So just depends on how you want to look at it. I probably should draw this more like that to show a half, and that to show more like a quarter. That would probably make a little more sense for you guys visually. Sorry about that. So we do times 2, and that's what you did before. So I got ahead of myself here. So then when you looked at Are You Ready for More, you looked at the same kind of idea. Okay, so that's what I was aiming at here. In the mixture A, this is a different one. I have 2 cups of water, so perhaps I just did this and said, here's a cup, and here's a cup. And then I had 4 teaspoons of salt. Teaspoon, 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 teaspoon. And this part here, a little tricky to draw, kind of with just a sketching of some sort. So maybe I just draw a long thing here that we'll use again and again for each one. This is a long element, long element. We'll pretend this is like 100 or something, okay? So it's a value of like 100. So this will be the halfway, halfway, halfway. And so 25 is going to be about there, 20.25. We'll come back to that in a second. Mixture B is going to be 1 cup and then a half of a cup. So about there, with 3 teaspoons, 1, 2, 3. And if I did my 0.25 there again, this is 0.2, that's going to be a little bit less than that, so somewhere about there. Again, this is just a quick sketch. And this guy is 1 cup and 2 teaspoons, and then not a 0.25, but half of that right there with a 0.125. This is 0.2. So in looking at this, the same idea, can you tell if there's something equivalent between these when you look at these two shapes? You know, to move from 1 cup to a cup and a half, or 1 cup to 2 cups, how would you do that, for example? That's the idea. So I could probably take a quick look, for example, at this one. To go from mixture C to mixture A, if I have 1 cup, to go from 1 cup times some number will get me to 2. Well, what would that number be? Well, we'd probably say a 2. Does this work for the teaspoons? Well, let's see. My teaspoon here was a 2. So if I multiply by the 2, well, how many do I end up with? 4. That seems to match. So that's working out well there. I could double check the sugar part, right? So the sugar, I had 0.125. If I multiply that by 2, 0.125 times 2 ends up being 0.25. And so that's a match. So I definitely can say that A and C are equivalent. That's for sure. But can I do anything with perhaps C and B? I'm doing C because it's starting with 1. It's a little bit easier to work with. So with C, if you had 1, I need to multiply by something here in order to get to, it looks like 1.5. Well, 1.5, we've seen this before. 1.5 can be rewritten. 2 times 1 is 2, plus 1 is 3. So times and add. So it can also look like 3 over 2. Okay? So can I get from 1 to 3 over 2? We've done that before. We know if we multiply, well, in this case here, I'm going to multiply by 3 over 2. So 1 times 3 over 2 gives me 3 over 2. So my common thing I'm multiplying by is going to be 3 over 2. So let's take a look then at the teaspoons. If the teaspoon was 2, now again we're looking right here at this one. If the teaspoon was 2 and I multiply by 3 over 2, I end up with 2 times 3 is 6, and the denominator stays at 2, which then reduces down 6 over 2 becomes 3. Okay, well that's matching so far, right? I can see that I went from there to there, okay, here to here, okay, no problem. But let's take a look at this last part, because all parts do matter. This is measuring, looking at the cups, this is looking at the teaspoon, but let's take a look at that sugar. The sugar here is a 0.125. I want to multiply by that same 3 halves. 3 halves can be written as a decimal, and as a decimal that is 1.5. Okay, so what is 0.125 times 1.5? Well, if it equals 0.2, then I have something I can work with. So 0.125 times 1.5 actually equals 0.1875. It needed to equal 2, so that does not equal 0.20. That's my big dilemma with this mixture B, is it's not going to have the right proportion of sugar. Is it close? It's certainly close, but it's not the same. We were good here, we were good here if this was our property or number we're multiplying by, but when we got to the sugar, it didn't work out. So it's a great question to make sure you work through the whole process and don't just say, well, that one works, I'm good. You really need to check all your details there to see if that's going to work. From that, you moved into a little section on the crescent moons. And so it began by saying, what do moons A, B, C all have in common that D does not? And perhaps you looked at them and you described them a little bit by saying, well, when I look at these shapes here, what I tend to see is these A, B, and C all seem to be like the same kind of height there and a similar width, all of them there, whereas D seems to be a little more squished down or pressed in. However you want to describe that there. You know, it's up to you how you want to look at that. You might eventually, with your class, have said, well, let's take a look. If I was to draw these in terms of being inside of a box, here's a width here, here's a width there, there's a width there for how wide those guys are. And I could take how long they are here, go down to there, drop down to here, drop down to here, and drop down to there. I might be able to notice that in letter A, moon, we go across 8 units across there. Here I go across 4. Here I'm going 1. Oops, what did I do there? Oh my goodness, sorry about that. I got ahead of myself. I go across, ignore. Here I go across 2. It's a fun part of math. You make mistakes sometimes and you just fix them. It's all good. All right, and I have 2 there, and this width right here is 1, 2, 3, 4, 5, 6. So in one sense you might look and go, well, it looks like I have a pattern 2, 4, 6, 8, but we can tell just visually that something funky is happening here with the heights of these shapes. Right, so with the small one, we're going 1, 2, 3. So there's my 3 right there. All right, over here with this guy, we're going 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Sorry, 6. And this one, 1, 2, 3, 4. This guy, we're going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12. So I now can kind of see that in terms of these shapes, if I was to make them go into a rectangle of some sort, like that, and put them in a nice little box, I have an 8 by 12 box here, I have a 4 by 6 box, I have a 2 by 3 box, and a 6 by 4 box right there. So I can see some things they have in common and don't, and I can use some numbers to describe how moons A, B, C, and D are different. Here's how you might want to look at it. See, this one here, A, is, if I'm looking at it in terms of a ratio of some sort, I might say that it has an 8 across to 12 kind of ratio there. I can look at this guy and say it's about a 4 to 6. This one is a 2 to 3, and this one is a 6 to 4. So even just looking at the numbers, we can tell one major difference without even doing any reducing math stuff. We just notice that in the first 3, A, B, and C, we always have a smaller number in the numerator and a larger number in the denominator. Where here, that's been reversed, hasn't it? So not even comparing how they're related, we can just visually see that this one has a small number, small, big, and we go big, small. Something's a little bit off there. But to prove that these are equivalent, you can use a tape diagram to do that, all right? As you can do a tape diagram, you can also do a chart. There's different ways to do that. So it says use a table or a double number line. If you did the double number line, perhaps you would look at something like the width of the object. So we had 2, 4, 6, so we can draw this like this. And we could say we had 2, 4, 6, 8, 2, 4, 6, 8. And then we could look at the height, how tall it is. And in our case here, the 2 went with the 3, the 4 went with the 6. We didn't have a 6, so we'll leave that blank for now. And the 8 went with the 12. And so for us, our little ratio here was 2 to 3. And to get from 2 to 4, it's times 2. 3 times 2 is 6. We're good there. To get from 8, it's 2 times 4. That works. 3 times 4 is 12. So if we were to have one with a 6, to get from 2 to 6 would be 2 times 3. And a 3 times 3 would end up with a 9 right there if we were asked to figure out what was missing. In our case, we had a 6 to 4. Well, 6 to 4 is definitely not 6 to 9, and that's why letter D, or moon D, was just not going to work. All right. You could also have done it as a table, it's a chart, and so you might have had the moon. You might have had the kind of the length here, and you might have had the width, which would be this direction there, with the length divided by width there. Okay, and you might have started with a small one and worked your way up, CBAD. And for C, our length is 2 with the height or width there of 3. And for B, we had 4 to 6. And A, we had 8 to 12. And D, we had 6 to 4. And so when you look then at what is that ratio going to be, we have length over width, which is 2 over 3. Here we have 4 over 6, which can be reduced to 2 over 3. Here we have 8 over 12, which can be also reduced to 2 over 3. And right here we have 6 over 4, which is reduced to 3 over 2. So that's our problem right there, is 3 over 2. These other ones are all equivalent fractions. They're all going to be the same, same idea. So the same fraction, 2/3, 2/3, 2/3, which is why C, B, and A are all going to be equivalent shapes there. They all are going to be very similar in that regard. All right. So that's what we did with the crescent moons there. So in summary for your lesson today, what we're talking about then is we're saying that when two different situations can be described by equivalent ratios, that means they are alike in some important way. So that's what we're talking about. The equivalent ratios means they're alike in an important way. This comes up a lot if you're dealing with things like a recipe, because if you make a recipe, you want it to be the same every single time. So when you make that recipe, you want to make sure that you have, if I make it at my house, then I make it at grandma's house, I want to do it the same way. Make the best cookies ever, but at grandma's house I use a different proportion of sugar or salt or whatever, it's going to change things. The idea being, how can I keep things the same? And so you end up with equivalent fractions and ratios here. A 3 to 1, a 12 to 4. These are all equivalent mixtures because if I'm going to look at 3 to 12, I'm multiplying by 4, and that's the same, and 1 times 4 is still there. I can also go smaller. I can reduce things. So let's say you're making some food at home, you don't want to make as much as the recipe calls for, you can cut things in half. In this case here, we're cutting a 3 into half, which means we have to cut that into half as well, or multiplying by a half like that. So lots of cool things you can do there, and a lot of real world application there as well. And so we apply that then to what we looked at before when we talked in Unit 1 about scaled copies. It's that same idea, right? Here I'm taking a picture and I have a length here of 3, and I'm taking it from a 3 to a 1.5, which means what? I'm multiplying by a half. I'm cutting it in half. Just like here, 2 to 1, same idea. I'm multiplying it by a half. Whereas here, I'm looking at it and saying, well, I'm going from 2 to 3. Now I'm making it larger, so it's going to be a number bigger than 2, greater than 1. So I'm multiplying it by a factor of 3 over 2. All right, because 2 times 3 over 2 is going to give me 3. So that's my scale factor there. So that's my scale copy, scale factors. But when you get to a guy like D, we recognize, well, 3 to 3 is the same, 2 to 3 is different. That's just not going to work. So when you do these shapes and you look at things, it's the same idea from the shapes that we're doing now with just numbers, and you can use a double tape diagram, you can use a table to prove those things there, but ultimately you're looking at things and making sure things align and they're working the same. Remember with these shapes that you are always going to have, when you have corresponding sides, that's important there. Remember we talked before about angles. Angle measurements are going to be corresponding too, but they never change their size. But that was from Unit 1. Let's move on to tonight's homework. Here we go. Now at this point, if you haven't started your homework yet, I'd recommend that you pause the video right here, just kind of push pause on it and start this on your own, and then press play once you think you've got it to check your work. Okay, so press pause. All right, and you're back. Here we go. So homework tonight, Unit 2, Lesson 1. One of these things is not like the others. Which one of these shapes is not like the others? Explain what makes it different by representing each width and height pair with a ratio. So here we go, looking at the first one. We can see, first of all, that we have some different shapes. All right, we have some different shapes here. And with this shape, number 1, we have a length across here, this way, of 1, 2, 3, 4, 5, going that way. And we have a height here of 1, 2, 3, 4. So 5 to 4 with that one. And notice with this guy right here, I'll draw on the bottom just so I don't run out of room. Going from edge to edge, I'm 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I have a height right here. 1, 2, 3, 4, 5, 6, 7, 8. 8. And my last one here, I'm also at 10, but I'm at a height of 1, 2, 3, 4, 5, 6. Okay, so that's what I have just visually so far. I have a 5 to 4, I have an 8 to 10, and a 10 to 6 is what I'm looking at there. It wants me to make some ratios and represent them to see which ones are equivalent to which ones. All right, so we could do this with a little chart like this. I can make a little chart to the side. I can say, well, let's look at shape A and shape B and shape C. And I can take a look at the width, how wide it is this way. Okay, and I can take a look at the height, how tall it is this way. And then I can look at my W over my H. All right. It's my width over my height there. I can take a look at that. So let's draw this down like this. Make a little table. And again, we said we were 5 and 4 for A. B was 10 and 8. And C is 10 and 6. When I do my width to height ratio, I have 5 to 4. I have 10 to 8. And I have 10 to 6. These both obviously have a 10 in the numerator with a different number in the denominator. And I want to show which one is going to be equivalent to the other one. So to think about this, how do you go from a 5 to a 10? I do that by multiplying by 2. That's what's going from a 5 to a 10. So to go from a 4 to something else, what is 4 times 2? 4 times 2 is going to be 8. So that would make that the right solution there, and this one would be incorrect. Not going to work. So the one that's going to match or be equivalent is going to be A and B are going to be equivalent. Can we see that in the picture? Yeah, we really do. We notice these look to be very similar in some regard. It's just a little bit larger version or a larger scaled copy of the shape. Our scale factor, if we went back to that, would be multiplying by 2 to get from there to there. For this one, we only multiplied the length of it, not the height, which is why that's not going to work for us. Okay, let's take a look at number 2. Number 2, it says in one version of a trail mix there are 3 cups of peanuts mixed with 2 cups of raisins. In another version there are 4.5 cups of peanuts mixed with 3 cups of raisins. Are the ratios equivalent for the 2 mixes? Explain your reasoning. I don't have a lot of space here to do this, but I think looking at the next question I can actually use this space down here, because I don't need any space for this next one. I can write it over there. So I'm going to put all my number 2 stuff right here. Okay, and use that space. So let's look at what we have. We have 3 peanuts. I'm going to write it as 3 peanuts, and I have 2 cups of raisins. So I have 3 peanuts for every 2 cups of raisins. Then on my next one, I have 4.5 peanuts and I have 3 cups of raisins. All right, so if this is my tape line, it's like I have a line here and I have a 3 and I have a 4.5, and my other line I have a 2 and I have a 3. And so the question is this going to work? Is this going to be an equivalent ratio? So here's my peanuts and my raisins here. That's the question. Is this moving in a proportional way? Is it an equivalent type of problem? So what you might want to think about then is, just like before, what can I multiply 3 by to get to 4.5? And if I don't know that, what can I multiply 2 by to get to 3? Okay, well, that's a great question. Let's start first of all with the raisins. All right, and now depending on which one you start with, you're going to work a different way. If I start here, I'm going to probably play with decimals. And if I start here, I'm probably going to play with fractions. I like playing with fractions. I know a lot of people don't, a lot of the kiddos, but fractions are kind of nice. Here's why. I could do 2 times some number is going to equal 3. Well, I can multiply 2 by 3 over 2 to simply get 3. Why? Because the 2's are going to cancel each other out, and so 3 will equal 3. So 2 times 3 over 2 equals 3. So now I have to use this same number and use it up here to see if these are equivalent. 3 times 3 over 2. Now at this point you might say to yourself, well, that's a fraction and you have a decimal as my answer I'm aiming for. I don't want to play that game. Sure, then don't play that game. Do you know what 3/2 is as a decimal? Perhaps you do. It's going to be 1 1/2, 1.5. If I was to do that as a mixed number, you'd have 1 1/2. So I'm just moving that 1 1/2 to 1.5. Now let's multiply 1.5 times 3 and see what happens. 5 times 3 is 15, carry the 1. 3 times 1 is 3 plus 1 is 4. I have 1 decimal, so I start here and I hop over and put it in place. And sure enough, 4.5 matches right there. So when I multiply by 3 over 2 and 3 over 2, I end up with 4.5 and 3, proving in a sense that these are going to be equivalent mixes. They're going to be the same proportion of peanuts to raisins. Even though I have different amounts, it's proportional. They are indeed equivalent. So we would say yes, these are going to be equivalent ratio mixtures because I have this factor here that I'm multiplying by 3.5 to demonstrate that they're going to be equivalent there. You could say you're multiplying it by 1.5 or by 3 over 2. Those are the same things. All right, so that was number 2. We just wrote it in the space for number 3, okay? Number 3, for each object, choose an appropriate scale for a drawing that fits on a regular sheet of paper. Not all the scales on the list will be used. So that's this one here. We're just deciding what kind of scale would I use to draw a person, for example, on a piece of paper. A regular piece of paper is 8.5 inches by 11 inches. 8.5 by 11, like so. The average person is not super tall. Let's just say anywhere from 5 to 6 feet. So we're just going to be switching things around from inches to feet. And that probably means we could just use the inch to feet one for a person. 1 inch to 1 feet, or 1 foot. We could do that for a person there. That's good to go. When I look at my other options, it gets a little silly because I have all these little things to look at. Football field, state of Washington, floor plan of a house, and a rectangular farm that goes by miles. Here I have 6 to 2 miles, 240 in yards. So when I'm looking at the size of things, this is my smallest thing in the whole mix. A house is the next thing, then football field, and then the farm, and then Washington. So looking at just the order of sizes helps me to start the scale process here, what's going to work. My choices, I have inches, centimeters. I have these unit ones that are just 1 to 1,000, 1 to 100,000, 1 to 10,000. So that could be interesting to play with there. I also have millimeters to kilometers. I could definitely see how that could work if I'm dealing with a large scale of something. That's a possibility there. This one here, I'm going to eliminate 4 as even an option. Why would I do that? Well, because my scale is 1 foot represents a mile. I'm dealing with a piece of paper that isn't even a foot long. So I can't even use that if I wanted to. So let's just eliminate number 4 as a choice. Let's not play with it, okay? Because there's no reason to. I can also take a look here and notice that something like 1 centimeter to 1 meter, that's going to be, there's going to be 100 centimeters equal a meter, right? So this is a small one compared to this guy here. This is 1,000. This is like a meter to a kilometer there. So there's some similarities there with this one to a meter to kilometer if you were using the meter unit, right? So anyways, let's take a look at what we have. So we have house, football, state, house, football, farm, and state in that order there. What I like to do is let's start with the floor plan of the house. Why? Because that's my next largest one. The floor plan of a house, well, if I'm looking at a piece of paper, a house isn't going to be super large, but probably with a house I'm going to measure it in terms of maybe meters, feet, and yards. Could I use an inch one? Probably not, because if I did the inch one, the largest my house could be would be 11 feet, right? That's probably a pretty small house. If I did this one here, 1 centimeter to a meter, my house could be 11 meters long. Well, could that work? Yeah, it could work. It might not be the a large house, but I could use meters there. And if I'm doing just different rooms, I could probably do that one. So for this guy, you might be able to do 1 centimeter to 1 meter. It could work. Okay, no problem there. So let's say we've got that one out of the way. So now I'm left with these other guys. What I like about these ones here is that they all seem to change the units based upon perhaps how ultimately large the object is. And so when I think about this, if I had a very large area I was trying to make a scaled copy of, I'd want to have a lot of numbers that I could then squish down into a little bit of space. Well, my largest one here is C with 240 miles by 360. So this might be a good one to use the 1 to 10,000 on, because it's my largest object. My next largest object is really the farm, 6 miles by 2 miles. Might be a good one to use the 1 to 100,000 on. And then if that's the case, I could probably use the 1 to 1,000 on the football field, possibly, right? Again, this is just what might you use. You're just thinking it through. So I'm just going to showing a couple of my strategies for how I did that there to say, well, I like these 3 units without all the unit things on, centimeters, meters, feet, miles, and I know that this is going to be used for a variety of things. This is my biggest shape, my medium shape, and my smaller shape. So that's kind of what I did. I just pulled those 3 out and said, let's use those 3 with these 3 items there, and then did the measurements for those guys there. Okay, number 4. For number 4, this goes back to unit 1, which scale is equivalent to 1 centimeter to 1 kilometer. So the way we do this here, if you think back to perhaps maybe with 6th grade, maybe something you did back there, is we could think about, well, how many centimeters are in 1 kilometer? So to do that, we have to set up our kind of conversion chart. So 1 centimeter is going to be the same as, well, let's do this. 1 meter, is the same as 100 centimeters. Not kilometers yet, so we're going to get there. 1 kilometer is the same as 1,000 meters. Okay, so these are our conversion factors. Conversion scales, or conversion. We're trying to get from centimeters to kilometers. So I'm multiplying 1 centimeter times 1 over 100 times 1 over 1,000 to see what I end up with. When I do that, 1 times 1 times 1 is 1, and 100 times 1,000, just put my zeros together, I have 1, 2, 1, 2, 1, 2, 3, 1, 2, 3, and insert the comma. So I end up with 1 over 100,000. Or, in terms of how this works here, 1 to 100,000. Is that an answer choice? Sure it is. Right here, choice C. 1 to 100,000. So that's the idea there. Okay? Now, if you said something like D, 100,000 to 1, well, that's going to be going the wrong direction, right? And that's thinking about, in one sense, you're on the right track there. You are thinking the right way. You are thinking, well, it takes 100,000 centimeters to make 1 kilometer. That is true, it is. But the way this is set up, though, is what scale is equivalent to 1 centimeter to 1 kilometer. We're going, in a sense, this direction. We want to keep it in that order. This one changes the order, okay? If it had been 1 kilometer to 1 centimeter, if that had been the question, then you would have done the other way, right? That would be 100,000 to 1. That's how that would work. But the question was 1 centimeter to 1 kilometer. So make sure you pay attention to that part there. And finally, number 5, find 3 different ratios that are equivalent to 7 to 3. To do this one, what I did is I just said, well, I don't want to spend a zillion days on this here, so let's do everything times 2. So if I did everything times 2, 7 times 2 is 14, and 3 times 2 is 6. So there's one. I could do everything times 3. So I write that again. So 7 times 3 is 21, and 3 times 3 is 9. I could do everything times 4. Right? And 7 times 4 is 28, and 3 times 4 is 12. If you wanted to have some fun, those of you that are going, I got this is too easy, could you use something besides a whole number? Could you go less than 1? Yep. In scale factors, we know we could go from a big shape to a smaller shape when we're using the scale factor. So sure, could I do 7 and a 3, and could I maybe multiply by a half? That'd be interesting, wouldn't it? If I multiply by a half, what could I end up with? Well, 7 times a half is going to be 7 over 2, which is 3.5. And 3 times a half, or half of 3, is 1.5. Does that work as well? Sure it does. As long as I'm multiplying both of those numbers by the same scale factor, it's going to end up with an equivalent ratio there, right? So why are these equivalent? They're equivalent because we're multiplying both numbers by the same scale factor, or we might want to say that the same, just the same multiplicative property. Okay, so sorry, early in the morning here. 2 times 3, 2 times 2 times 3 times 4, or times a half. They all work out great. Hope that helps with your homework today. Good luck, and ask your teacher questions if you have more. Have a great day.